So good morning, everyone, and welcome to the 2024 Cheriton Research Symposium. My name is Rauf Boutaba, and I'm currently the director of the Cheriton School of Computer Science. So it's really nice to see you all here gathered to celebrate research excellence. As you may know, and some of you are new here, our school owes its name to David Cheriton, who's one of our distinguished alumni, received his PhD from this school back in 1978. And back in 2005, David made a substantial investment in computer science that transformed our school and elevated its research stature. So this investment led to the creation of the David Cheriton Endowment for Excellence in Computer Science. And this endowment has been used to recruit two Cheriton chairs, namely Jimmy and Ashokan. And it is used every year to appoint Cheriton faculty fellows. Cheriton fellowship is held by leading faculty members in the school for a term of 3 years. And it has been also used to give away scholarships to excellent graduate students. And today, we will hear from two Cheriton faculty fellows, namely Eric Blais and Semi Salihoglu. And new in the symposium this year, we will have a panel discussion, which will be moderated by Dave Tompkins on the future of CS educations. And we will have as panelists David Cheriton, Gordon Cormack, and May Nagapan, and Carmen Bruni, yes. And I think it's a very timely discussion to have, considering the recent development in online learning platforms and Gen AI tools. And look forward to that discussion indeed. And after the panel, we will have a break, lunch break in the fishbowl next door. And after the lunch break, as usual, we'll have the poster sessions where some of the awardees of the Cheriton Scholarship will present their work, starting, I think, after 1 p.m. And then we will reconvene here around 4 p.m. for the awards ceremony and an opportunity to give prizes to the best poster presenters. And as it is the tradition, we will be serving gelato at that time. So hopefully we'll see a lot of you there. And that's for the schedule of the symposium this year. So without further ado, let me introduce our first speaker, Cheriton Fellow Eric Blais, who's also Associate Professor in the Algorithms and Complexity Group. His research spans theory of computing, and with particular interest in sublinear-time algorithms, randomness in computation, and complexity theory. So he received the prestigious Fox 2020 award for work done with one of our other colleagues, Shalev Ben David, in extending the Yao's min-max theorem. Big achievement there. And so Eric received his PhD from CMU, and he did a postdoctoral fellow as a Sloan, I think, fellow at MIT. And yeah, that's it for the introduction. So please come over, Eric.
Thank you, Rauf. Is this working? Right level? Good. What I want to talk about is actually very different work from this min-max theorem. It's work that was done with Cameron Seth, one of our PhD students here. And what I really want to do is not so much cover the technical details of that work as to explain to you and hopefully show to you why I'm excited about this work. And I guess the main reason I'm excited about it, it's because in algorithms and complexity theory, there are these problems that just show up over and over and over again. And the more we study them, the more we realize how much of a central role they play in computer science and understanding what we can solve efficiently with computers. And one of those problems is the independent set problem. So I have a graph. A set of vertices in this graph is an independent set if there's no edges between any of those vertices in the set. If you like cliques, edges that, vertices that are all connected by edges in the graph, this is going to be equivalent to independent sets in this in all the problems I'll cover just by taking the complement of the graph. So if you don't like independent sets, feel free to switch with clique in your mind the entire time. But for now, I want to say, okay, I'm going to look at independent sets, and the most natural question I can ask is, if I give you a graph on n vertices, and I give you a number k, I can ask you, does your graph have an independent set of size k? This is the independent set problem, and there's many different variants that you can think of it. What I'm really going to be thinking about here are fairly dense graphs, graphs that have lots of edges in them, and where I'm looking for large independent sets. So I'm going to keep on saying k, but you should think of k not as a constant, but as some function of n. So maybe square root n, or maybe even a constant size n. I'm looking for fairly big independent sets in what I'm thinking of. Okay, so why is this a central problem in computer science? Reason number one, it's because it shows up everywhere. It shows up whether or not what you study actually directly is related to graphs or not. It shows up in hiding over and over again. For example, it shows up in the flashlight puzzle that I just happened to come across right before I had a driving trip, and I'm like, great, this is something I can think about without actually using paper. I can try to figure out the answer to this problem while I'm driving as a distraction. It's not too distracting, so I managed to make it here. But it's a nice problem. So you have 4 good batteries, 4 bad batteries. You don't know which is which. You have a flashlight, and you're going camping, and you want 2 good batteries in your flashlight. So what do? You keep on 2 batteries and seeing if it turns on or off. It only turns on when you have 2 good batteries. So now the question is, okay, what's the most efficient procedure that will guarantee that you find 2 good batteries and your flashlight turns on and you're ready to go? Has nothing to do with graphs, except it does. It's a graph problem in hiding. Why? Because for every battery, I can think of these as a vertex on a graph. Now, what does testing 2 batteries with my flashlight actually mean? Well, I can represent it as an edge between 2 vertices. And so if I decide to test these 2 batteries, that corresponds to an edge. And what's going to happen when I actually run this test is it will not light up if one of those batteries is empty. But on the other hand, if I test 2 good batteries, then it will light up. So now you claim you've gotten a solution to this flashlight puzzle. What does that actually mean? Your solution, you tell me, oh, I'm going to take the 1st and 3rd battery, test them together, and then I'm going to take 3rd and 5th, test them together. You can actually represent your strategy as a graph. And your strategy is going to be a valid strategy if wherever I put the good batteries, you have at least 1 edge between those vertices for the good batteries. So your strategy is going to be valid if and only if your graph has no independent set of size 4, the graph for your procedure. So here was a problem about batteries, has nothing to do with graphs, but in fact, it has everything to do with independent sets, just in hiding. Okay, so that's just one example. It's a toy example. There is lots of other examples everywhere that would be much more serious that we could come up with, but let's just move on for now and say, okay, yes, independent set, great. So let's just solve this problem. That's fine. There's a very simple algorithm that you've all seen. It might hurt your eyes to see this algorithm because it's the brute force algorithm. Just go over all sets of k vertices and then check if there's no edges between them. And if you ever find an independent set of size k, you're done. Congratulations. And if you've gone through all possible places where you could place k vertices and find an independent set, and all of those sets have an edge between them, then you can confidently say, yeah, you don't have any independent set. I say this algorithm is painful because, I mean, for lack of a better term, it is so stupid. There are so many ways that you can think immediately off the top of your head on how to prune part of this search tree. It's being really wasteful in many ways. And so it seems obvious that we can do better. And in fact, if k is very small, like looking for triangles in graphs, there are faster algorithms. Now, if you know fast matrix multiplication, you can actually apply tricks to provably get something better than this brute force. But here I'm thinking of k is large. K is large means things are really bad. We don't have polynomial time running time here, just because there's too many possible sets to look at. And so the question becomes, can we actually be clever and get something that runs in polynomial time? And the answer famously is no. You can do better than brute force, but you can't do much better than brute force unless p happens to be equal to np. So this was one of the 21 initial problems that Karp showed were NP-complete in the very famous early paper that launched a lot of the research in NP-completeness. So unless you set out to prove something really impressive, I don't recommend trying to actually develop a polynomial time algorithm for independent set. Of course, as computer scientists, we know that's not the end of the story. That's fine. We know how to deal with NP-hard problems. One of the ways we can deal with them is to try to figure out how to relax them, how to have approximation versions of these problems. So maybe sometimes what you don't really need is the exact size of the largest independent set in your graph. Maybe you don't really want to know if it has an independent set of size k. What you really want to know is if there's a really large independent set of size k, or there's only really, really small independent sets of size j for some j much less than k. So it might be that you're happy where if you're in between the two, any answer is fine. What you really are worried about are the extreme cases. You want to be able to distinguish between them. So okay, I'm asking you to find large independent sets versus graphs that don't even have small independent sets. That should be very easy. It is not. Essentially, this is different than P versus NP, but conceptually, it's the exact same thing. You will not only not be able to solve this problem with constant factor separation, you won't be able to distinguish graphs that have almost linear size independent sets from those that have almost constant size independent set, like n to the 0.99 versus n to the 0.1. Can't even distinguish this in polynomial time. So even this approximate version of the problem is hard. And this is where this problem becomes fun, because you're like, okay, that's a little bit disappointing, but it's fine. We can define other approximation versions of the problem. This is the one that I really like. It says, okay, forget large versus small independent sets. The right way to relax this problem is to say, okay, I just want to be able to distinguish the graphs that have a very large independent set from the graphs that are far from having large independent sets. What does that mean? It means for any set of vertices that you look like, it really does not look like an independent set on k vertices. It has to be very dense. So now I have this task where one type of graph has a really large independent set somewhere, and the other type of graph has lots of edges. Anywhere that you look, it has tons and tons of edges. So come on, this is easy. Yeah, of course, the punchline is nope. No, this is hard too. We believe this is hard. This is kind of weaker or stronger assumption. So it's a weaker result than P versus NP, but essentially the punchline is it would be extremely surprising and a huge breakthrough if you could solve this problem for some reasonably large k, even when you're looking at an independent set versus really dense graphs. I said the constant density, it's even more than this. So even this version of the problem is hard. And if I had more time, I could show you like lots more ridiculous versions of this problem where it becomes easier and easier still than this. And it still is essentially open whether we can do any of those in polynomial time. So yeah, so this is why my title of the talk, testing independent sets with your eyes closed. It's an easy thing. No, it's the hardest thing you can do. I can't think of any harder problem. And yet, is it actually that easy, that hard? There was a fantastic question that Oded Goldreich, Shafi Goldwasser, and Dan Aron asked in the late 1990s. They said, okay, let's forget about running time for a second. Let's ask seemingly an even harder question. If I'm trying to do this testing independent set problem, one, you have a large independent set, versus two, all your graphs are quite dense, can I do this without even looking at the entire graph? Can I do this with my eyes closed? Can I do this by just sampling a tiny, tiny fraction of the graph? So small that, yeah, okay, I can run my really expensive algorithms on this small graph and somehow be able to deduce, oh yes, I was looking at a graph that originally had a really large independent set, or no, actually I'm looking at a graph that does not have any large independent set. I say this is an amazing question to ask because everything we've seen up until now kind of suggests don't ask about anything being easy. Everything is hard with independent sets. But this is not hard. You can do this. This amazing result they showed, okay, if we're looking at really large cliques or independent sets, if we're looking at independent sets of size, say, n/2 or some constant fraction of n, and we're trying to solve this problem, do you have a large independent set versus are all these very large sets quite dense? You can actually do this by sampling a constant number of vertices and just checking, looking at the graph between those vertices, and then just outputting your answer. And you'll be correct most of the time. This is amazing. We've gone from this is NP-complete to actually for this version, for very large independent sets, we can do it in constant time if you can assume that just sampling takes constant time. So this is the starting point of a whole bunch of research. So this research actually led to advances in all these different areas. This is a sampling of them. I could go into details, but it's been extremely influential in part because this is so surprising that we have this result, that this is possible at all. What I want to do, though, is not to go into any of those. I want to go back to their theorem. Because it's amazing what it says when you're looking at independent sets that are extremely large, that are a constant fraction of the graph. But it's natural to ask, okay, what about like slightly smaller independent sets? Can we still do something kind of amazing? Can we still sample a sublinear fraction of the graph? Look at it. Not even 1% of your graph, and yet still be able to tell if you had an independent set or if you were far from it. And if you work through the details of the proof, you see that their result actually says, yes, you can do this for quite large cliques, for independent sets. For independent sets of size at least n to the 6/7. So some polynomial in n, you reach this threshold, and anything bigger than this, we can solve by just sampling a really tiny fraction of the graph. Okay, but n to the 6/7, that's not going to be the right answer. There's no way that's the best we can do. There's no reason to believe there should be some change in behavior when we're looking at independent sets smaller or bigger than this. And sure enough, a few years later, a group of authors showed that actually we can improve the results to show that anytime you're looking for an independent set of size more than √n, then we can do this in sublinear time. We can do this by sampling a really small fraction of the graph. This bound, there's actually lots of good reasons to believe why it might be the right bound. I haven't gone into the details, but this √n shows up over and over again as kind of a special threshold when studying independent sets. So there's this question, is this actually the barrier, or can we still test independent sets even when we go to smaller independent sets? This is what we set out to study, and what we showed is actually it's not a barrier at all. You can go essentially as small as you want, really small, up to logarithmic size, and those independent sets, even those small independent sets, we can actually test if you have them by sampling just a tiny fraction of the graph. So this is a really nice, really surprising result. And what I want to do is give you just a quick idea of how we prove this, because there's yet one more reason why I really like this result. How would you go about proving these kinds of things? What you'd want to say is, okay, if I sample a graph and you had an independent set that was quite large, I'm probably still going to have a large independent set in whatever I sample. That's just standard concentration inequalities you'd use, and you'd say, okay, yes, this is easy. We can prove this. So now on the flip side, you'd want to say, okay, whenever I start with a graph where all the subgraphs are dense, when I sample a graph, I'm not going to have a large independent set. I am very unlikely to actually sample a very large independent set from this original graph. This is the natural tester. This is what you'd want to do to prove all these theorems, starting from Goldreich, Goldwasser, and Rahn. This is not what they did. They tried this. They could not do it. And the reason they could not do it was essentially the same reason why the brute force algorithm is so bad, because there can be too many places where you can have independent sets in a graph. And in this case, you can have too many independent sets. Even if I promise you that all the K-subsets are all dense, you can still hide smaller independent sets and too many of them for the math to go through, essentially. And so what they did is they had to go through a very complicated, different argument. They used different algorithms, and then they show, oh, so this works, so that's how we can test it. Feige and company, their improvements, something similar. They, again, have to go through a lot of gymnastics to kind of show that the algorithm works. And it's not the natural argument you would want to kind of have be the right argument. And what we've been able to show is this great surprise to us, that actually you can use this idea. The problem was you can have too many independent sets in your graph, even if you promise me that it's far from having very large independent sets. You can have independent sets that are just a little bit smaller, and you can have lots of them. And yes, so now this doesn't work. But if you have a lot of independent sets in your graph, and all your K-subsets are quite dense, you cannot have your independent sets just anywhere in the graph. They have to have some structure. They have to be kind of clustered together. So we have this situation where if you don't have too many independent sets in your graph, it's great. Everything works by a simple argument. And if you do have a lot, then we have a container lemma that shows if you had a lot, they had to be clustered together into very few containers, subsets of vertices where all the independent sets are contained in one of those containers. And now we can actually use morally the exact argument we wanted to use on independent sets. We just use it on containers to say, oh, you're very unlikely to actually include enough vertices from a container to even have an independent set in there. So this is it. This is all I wanted to say about the proof itself. If you remember anything about this talk, remember the word container. Maybe picture a container ship right now, so that the next time you find yourself looking at independent sets popping up at an inopportune moment while you're doing research, you can say, well, maybe the container method might help. It has been a tool that very recently, throughout many different areas of mathematics, has shown to be useful in surprising ways everywhere, exactly because independent sets show up everywhere. Okay, so then what can I say? I can say once you have this, actually that's not the end of the story. That's really the beginning of the story. There's many other properties we can show that we can test by just sampling a very small fraction of the graph using this container method. We can look at hypergraphs. We can look at satisfiability. We can even get some other surprising results, like saying, hey, sampling a subgraph and then querying everything in the subgraph. If I'm charging you for every pair of vertices that you ask if there's an edge or not between them, is that the best thing you can do? We showed for the first time, no, that's not the best thing. There's something better that you can do that would have fewer total queries than just looking at a subgraph. Yeah, and this is kind of the story. We have lots of things. And there's lots of things we're still hoping to get, or hoping someone gets. The most obvious one of all being, I talked about how, for running time, we have all these hardness results. And we do get some running time results if you apply the sampling approach just based on the fact that we're looking at smaller graphs, but we don't really have faster algorithms in a way that I find really meaningful. I think there's a lot more to be said about what kind of fast algorithms we could design if we can use this subsampling or if we can use containers more effectively. So this is the big question I want to leave open for now. And this is everything I wanted to tell you about independent sets for today. If you do want more, if you want the details, There's 2 archive preprints, or the conference version of the paper if you want to look at them. And Cameron actually has a great YouTube video actually stepping through the proof if you want to learn more about what the container lemma is. So I highly recommend those 2 sources. Thank you.
From about the second example, after the brute force algorithm, you jumped to things where it looked like to me where probabilistic methods would work in polynomial time. Then several examples, and then bang, oh, you hit one that, oh, probabilistic algorithm works in constant time. Was there a general speed up of those algorithms of possibilities as you bounced along? It just sort of jumps out in hindsight.
Yeah, this is a great question. Where did we get this jump from can't even do it in polynomial time to constant time? In a very abrupt way is the answer. It's not smooth. So all those hardness results that I mentioned apply to randomized algorithms as well. We know randomness will not help. But they only apply when you're looking at independent sets that are sublinear size. So you cannot be a constant fraction of the graph. In this one special case, we do know how to do it, I believe deterministically even, in polynomial time. And so the result that we get from Goldreich, Goldwasser, and Rahn is that actually for this setting with randomness, you go from polynomial time to constant time. But as soon as you shrink below linear time, all bets are off. We still do not have polynomial time algorithms anywhere. So this is really, this jump is the boundary that's most exciting to try to understand for time complexity for faster algorithms.
So you could regard your independent sets as defined in terms of a distance greater than 1 between these nodes, vertices, right? So has anybody looked at the generalization of a greater distance greater than that? Like supposing I say it's got to be very independent sets or distance.
That is a fantastic question. So the question is, what happens if we think of this as distance and we ask about distance more than 1? The quick answer, the honest answer is, that's a great question that I never thought about. I thought what you were going to ask was something slightly different, where we can think of edges as coming from a set where points that are at distance more than 1 do not have an edge, and points that are close together have an edge. That's a lot of times how we get these graphs. And those, I was going to warn, all my hardness results might go out the window because now we have very structured classes of graphs. But what you're asking is something very different. No, just what happens when I define a very independent set. And I don't know what happens then. Yeah, no, I was going to hazard a guess, but I won't even hazard a guess. So eventually it has to become easy, but the question is going to be, yeah, do we have the same kind of fall off a cliff the moment you go from constant to super constant, or could you actually even, or even linear to sublinear? I don't even know where the hard region would be. That would be, yeah, that'd be really interesting to figure out.
Edges are matters too. Length.
So now this is, yeah. And actually, for everything I've said now, the notion of what it means to be far from having these very independent sets also becomes tricky. I think there's a lot of, yeah, I don't know. Great to tell me the answer to.
It's the case that I think almost all graphs have diameter 2, almost all random graphs, right? So I don't know if this has direct bearing on the question, but
yeah, so right, the
axis.
observation here that, well, maybe if we look at almost all graphs, random graphs satisfy this very small diameter property. One thing that's very nice about this line of work is that all the results are really easy when I'm asking about almost all graphs. And what really becomes tricky is if I'm not looking at random graph, I can have this weird kind of structure that's kind of going against my algorithms that makes things much different. I don't know if this is the case for this problem. It might also be that actually just because of reasons like this, it is very easy as soon as we look at higher diameter.
Hi, Eric. So I wanted to ask something about the sequence of results. So you had a result for test independent set, the first original result, I think from 98, that said n to the 6/7. If there is a very large independent set with constant size sampling, you can tell it. That went down to square root of n, and that went down to polylog n. So in all of these cases, though, you're always sampling a constant size. Is that
No, so here these results are for sampling sublinear size. So sampling a subgraph of size little o of n, but much bigger than constant. So n to the 0.99, for example. So it's saying if I relax from wanting to sample a constant size graph to just n to the 0.99, when can I actually do this? And those results show you can do this as long as you were looking for independent sets of those sizes.
okay? But so for independent sets that are greater than polylog n, you are able to tell if there is such a independent set with very small sampling, constant size sampling. Is that the wrong interpretation?
With sublinear size sampling, which I still consider to be almost constant. As your graphs grow to infinity, it's a smaller and smaller fraction of the graph, but it's very different than constant size.
Okay.
So yeah, it is not
It's
constant.
not constant. Okay.
That would be only for linear size, nothing else
Okay.
we can do
All
with
right.
this. Thank you.